Welcome to today's Explainer. We're diving right into the high-stakes cyber arms race happening right this second inside your computer's memory. It's a battle that operates in milliseconds, yet it's the exact mechanism keeping your personal phone secure and your bank data safe from hackers. For decades, software has been absolutely riddled with bugs, and attackers have exploited those bugs to hijack systems. But how do we build robust security architectures when we know fundamentally that the legacy software we rely on is just flawed? Right, so that is the core dilemma. We have massive amounts of legacy C code out there running basically the entire world, and it is inherently vulnerable, and we can't just rewrite all of it overnight. What's super fascinating is that security engineers have to treat this almost like a natural science. They study the ecosystem, observe exactly what the attackers are doing out in the wild, and then build highly specific defenses around those exact behaviors. But to understand the defenses, we first have to understand the attack.
Section 1. Anatomy of an exploit. The heist plan. Okay, let's dive into this. To steal the contents of a vault, you need a highly specific plan. And in the software world, that's the classic buffer overflow attack. Here's the exact roadmap an attacker uses to hijack a program. It's really just a three-step process. Step 1, the attacker overflows a memory buffer and overwrites the return address on the stack. Step 2, the program unknowingly uses that corrupted address and jumps to a location chosen by the attacker. And step 3, the program executes the attacker's malicious machine code, often called shellcode. Basically, every defense we're about to look at targets one of these specific steps to try and break the heist.
Next up, locks and tripwires, the first layers of defense. The absolute easiest way to stop the heist is to block that final step, the execution, by enforcing a strict rule where memory can be writable or it can be executable, but never both. But of course, attackers adapted. So defenders introduced a way to catch the heist at step 1, using a stack canary. It's honestly amazing how simple yet effective this is. The compiler automatically inserts a randomized value onto the stack right in front of the return address. It's a literal tripwire. If an attacker overflows the buffer to reach the return address, they have to blindly overwrite the canary too. Right before the function returns, the system checks the canary. If it's corrupted, the system panics and terminates the process instantly.
Yes, this seems like a totally airtight defense. But as always in this arms race, we have to ask the attacker's favorite question. How do you defeat a seemingly perfect random lock? Well, the answer lies in how some servers fundamentally operate. It turns out, perfectly random locks aren't actually so perfect if the server just keeps handing out exact copies of it. Many Unix network servers use what's called a fork model, where they copy their entire memory space for every single new connection. That means the supposedly random canary gets copied exactly, over and over again. So an attacker can connect, overflow just one byte into the canary, and wait. If the server crashes, they guessed wrong, so they try again. Because a single byte only has 256 possible values, an attacker can brute force a 4-byte canary in just over 1,000 tries. Once they know the canary, they can forge it perfectly and just continue the heist.
Moving on to the memory shell game. Address Space Layout Randomization, or ASLR. Since tripwires clearly aren't foolproof, defenders had to change tactics by constantly moving the vault itself. Every time a program starts, the operating system randomly scrambles the locations of the stack, the heap, the code, and the libraries. The attacker can't just jump to a predictable memory address anymore because they have absolutely no idea where their malicious shellcode is actually located. They're flying completely blind. But remember, attackers are incredibly clever. Their countermove to this randomization is something called the NOP sled. NOP stands for no operation. It's an instruction that basically tells the computer to do absolutely nothing and just move to the next instruction. Now, a NOP sled might sound like a fun winter activity, but it's actually a devastating way to slide right into a malicious payload. Attackers literally spray megabytes of these empty NOP instructions into memory, with their actual malicious code attached at the very end. Then they just guess a random memory address. If they land anywhere inside that massive sled, the computer just slides seamlessly down the empty instructions right into the attack.
Which brings us to the fat pointer problem, the ultimate heavy vault.
All these tricks, canaries, ASLR, they make exploiting a buffer overflow much harder, sure, but to truly stop the root cause, we really need bounds checking. The theoretical ideal to stop this is something called a fat pointer. In memory-safe languages like Rust or Go, a pointer isn't just a single memory address. It's a bulky structure that carries the actual pointer, the base start address of the object, and the limit.
Every single time the program tries to access memory, the system checks, is the pointer between the base and the limit? If not, it safely stops the program. It literally solves the buffer overflow problem instantly. But here's the fatal friction. Fat pointers are brilliant, but they completely break legacy C code. A lot of old software expects a pointer to be the exact same size as a standard integer. If you suddenly triple the size of a pointer to include base and limit bounds, you don't just break a program or two. Breaking millions of lines of existing C code means basically breaking the internet's infrastructure overnight.
Next up, baggy bounds checking, the clever compromise. This brings us right to the climax of today's explainer, a highly optimized bit hacking trick designed to give us the security of a heavy vault without all the bloat. Instead of carrying the base and limit data inside the pointer, baggy bounds forces the system to allocate memory in strict power of two sizes, like 64 bytes, 128 bytes, or 256 bytes. Think of it like perfectly sized shipping containers. Because the system knows the standard size of the box and knows it perfectly aligns in memory, it can use simple math to instantly calculate the base address. You don't need to store the base address anymore. The math predictably derives it for you on the fly. To store the limits efficiently, baggy bounds uses a minimum slot size parameter of 16 bytes. It's actually wild. By doing this, they compress the tracking table massively. The system only needs to store one tiny byte of size information for every 16 bytes of real memory. It's incredibly light, it's incredibly fast, and best of all, it keeps the pointers at their standard size. But there is a ridiculous, yet very real hurdle. The C programming standard legally requires compilers to allow pointers to step exactly 1 byte out of bounds. This happens when developers write code that iterates through an array backwards. It's highly ironic that the standard legally forces defenders to intentionally let pointers step out of bounds. The defense system can't just panic the millisecond a pointer crosses the line. So this poses a massive technical puzzle. Think about it. If you intentionally let a pointer step out of its designated memory boundary, how does the system track it without confusing it for a totally valid pointer belonging to the completely separate memory object sitting right next door? Here is the brilliant hack. You flip the highest bit. When a pointer steps out of bounds, baggy bounds instantly flips the highest bit of the memory address. This immediately invalidates the address. If the program actually tries to use this out-of-bounds pointer, it triggers a safe crash. But the lower bits still retain the exact mathematical offset. So if the C code iterates back into bounds, baggy bounds simply unflips the bit almost like a magic trick, and the program continues running perfectly as if nothing ever happened. It's just an incredibly elegant solution for legacy systems. But as we know, this is a never-ending arms race. Techniques like baggy bounds have made classic buffer overflows incredibly difficult to pull off today. But if we close the door on bounds checking, what do attackers exploit next? Well, the answer lies in the dimension of time. Use after free bugs, where a program legally accesses memory, frees it, but mistakenly keeps using it after another program has already taken it over. Before we wrap up, just remember why all this matters. This invisible arms race happening right under our noses in milliseconds is literally the only thing protecting our digital lives today. Thanks so much for joining me on this explainer. I'll see you in the next one.